Okay, so here we are in section 4.3, and this section is going to be really important in the rest of chapter 4. And the reason for that is because we're focusing strictly here on homogeneous linear equations with constant coefficients. And if you recall, from what we talked about back in 4.1, when we're looking at the more general non-homogeneous case, solving linear equations, we need both a complementary solution and a particular solution. And that complementary solution is, remember, the solution to the associated homogeneous linear equation. So, typically when we're talking about linear differential equations, whether it's homogeneous or non-homogeneous, we always start by looking at a homogeneous equation that's related to it. So the work that we do here is going to be relevant again and again throughout chapter 4. But we're focusing on the simplest type, like I said. We're focusing on homogeneous linear equations where the coefficients are just constants. It turns out that we can pretty easily come up with a really nice way of solving these things. Now, chapter 4, our focus is higher order differential equations. We spent all of chapter 2 looking at first order equations. And what I'd like to do is use a first order equation of this type. So a linear, homogeneous first order equation where the coefficients are all constants, and use that for inspiration to figure out what we might want to try doing in the case of a higher order differential equation. And we're actually going to focus on second order equations for the most part, and then we'll talk about even higher ordered at the end of the section. So here is what a first order linear homogeneous differential equation with constant coefficients might look like. A and B are going to be assumed to be constants, and A is going to be non-zero, because if it's equal to 0, then we don't even have a first order equation. We just have an equation for y. Being linear and also being separable, it's easy enough to see that this is a separable equation. We could solve it using separation of variables or integration factors or integrating factors. But even if we just go from intuition, there's actually an easy way to find a solution to this. Let's take this equation here and solve it for y prime. You're going to get y prime equals negative b over a y. Now think about this just based off of calculus 1 level knowledge. What we're looking for is a function y whose derivative is a constant multiple of the original function y. So in other words, can you think of a function such that when you take the derivative of that function, the result is just a constant times that original function? Well, in calculus 1, you spend plenty of time looking at exponential functions which do exactly that. The function y equals e to the mx, its derivative is equal to that constant m times itself. Its derivative is a constant multiple of itself. In this particular case, if I'm looking for a solution to this, that m that would be appearing here is just negative b over a. But the point is that it's a constant. So even without separation of variables or integrating factors, you can come to that conclusion pretty quickly. Now, that's for the first order case. What about the second order case? Well, I want to make a little disclaimer here because this is where people get a little, I think some people get a little uncomfortable with how we approach certain solution methods. If you've done much math up until this point, which you would have had to get here, you've seen some amount of mathematical proof. If you've taken linear algebra, you've seen much more than the average student who's in this class. And a lot of mathematical proof that you would have seen up until this point is deductive. So basically you start with some initial assumption and then you follow only a sequence of logical steps to reach a conclusion. And some of our solution methods for differential equations operate the same way. The way that we derived a solution for a separable equation using separation of variables all the way back in chapter 2, that was kind of a deductive approach. But oftentimes we don't get very far with that approach in differential equations. And what we sometimes do instead is we just try and throw whatever we can at a differential equation until something sticks. Okay, and so what we're going to do here is I'm going to start with this general second order linear equation. It's homogeneous and it has constant coefficients. And I want to see what happens if I try testing out a solution of this type. It seemed to work in the first order case. Maybe an equation, or maybe a function like this one will work as a solution in the second order case. We just try it and see what happens. So what I'm going to do is assume that this equation has a solution of the form y equals e to the mx, an exponential function. And then I want to see if that's the case, what can I say about this equation after plugging that solution in? So if I were to take this solution, y equals e to the mx, this function, and plug it into this equation, I know that y prime would equal m e to the mx, and I know that y double prime would equal m squared e to the mx. So that's what needs to be plugged in for the y double prime, the y prime, and the y, those three respective functions. Okay, now if you look at what's become of my differential equation after plugging in that assumed solution, is I have an equation where each term has this common factor of e to the mx. I can pull that e to the mx out, and look what's left here. E to the power of mx times a quadratic equation in the variable m equals 0. The constant m here is what I'm trying to solve for. I would like to know what m needs to be specifically in order for this thing to have been a solution to that original dE in the first place. Now I know that exponential functions are never equal to 0. So there's no hope of this factor giving me 0. That means that if this is true, that quadratic right there has to equal 0. And so what I do is I set am squared plus bm plus c equal to 0. And we call this equation the auxiliary equation for that dE. I'm not 100% sure I pronounced that right. Auxiliary. Whatever the solutions to that quadratic equation happen to be are going to provide us with the values of m that we can put here and give us solutions to that dE. Okay. Now, with that said, what do we need to get a general solution for a homogeneous linear dE? All we need are for a second order. Because remember, we're focusing just on the second order case right here. What do I need for a general solution to a second order homogeneous linear equation with, I don't even need the constant coefficients condition for this part. What we need are two solutions that are linearly independent, and then the set of all linear combinations of those will form our general solution. So fortunately for us, quadratic equations will oftentimes produce two solutions, and those two solutions, when put into y to the mx, if they are linearly independent, the set that they form happens to be linearly independent, then we can use that to find our general solution. But that's not always the case. So what we need to do is look at all possible cases for the solutions to a quadratic equation. This is something that you should have discussed in algebra when you talk about the discriminant. If you remember, for any quadratic equation, the discriminant is defined to be b squared minus 4ac. It's the thing that appears under the radical in the quadratic formula. And whether that quantity is positive, negative, or equal to 0 determines what we can say about the roots of that equation. So if b squared minus 4ac, your discriminant, is positive, then there will always be exactly two distinct real solutions. We're going to think of that as case 1. We'll look at that in more depth in a second. Case 2, the discriminant equals 0. When that happens, you have exactly one real solution. We call that a repeated root, because what that implies is that if you were to factor this quadratic down in the case where you have a 0 discriminant like this, the factored form of this is going to look like a binomial squared. And so that binomial squaring that is giving us a repeated root. If the discriminant is negative, you get two distinct complex solutions. And not only that, we also know that the complex solutions will be conjugates of each other. We say that the solutions come in conjugate pairs. So I want to take a look at all three of those cases to see what we can do to solve these homogeneous second order linear DEs with constant coefficients. It's so much to say all that every single time. Case 1. If we have that DE that we talked about and our auxiliary equation has two distinct real solutions. So this is the case where the discriminant is positive. What can we say about our solution set? Well, let's suppose that the two real solutions that were guaranteed by this are M1 and M2. Okay? So based on the previous discussion, that means that y equals e to the m1x and y equals e to the m2x are both solutions to this differential equation. Now this thing may have lots and lots of different solutions, but all we need to be able to do is determine two of them that happen to also form a linearly independent set. And we can test this for linear independence by using our Wronskian. So here's the Wronskian of these two functions. It's this determinant here, and if you evaluate this determinant, it's an easy one to do. You get this, m2 minus m1 times e to the m1 plus m2x. Remember, if we want these two functions to form a linearly independent set, then we need this to be non-zero. Now, e to any power, as we've already said, is never equal to 0, and m2 minus m1 also can't equal 0 because we assumed in the first place that these are distinct real roots. If m2 minus m1 equaled 0, then that implies that m2 equals m1, which we assumed was not the case. So this is non-zero, giving us the linear independence that we need to say what our general solution is. So now that we've established linear independence, our general solution for the DE that we showed on the previous page is y equals c1 e to the m1x plus c2 e to the m2x. The m1 and the m2, again, are just the solutions to that auxiliary equation, okay? I want to go through all three cases before we look at any examples. In fact, we might not even get to any examples until the second video, and that's fine. What can we do in the event of case 2? So if our discriminant for our auxiliary equation is equal to 0, that implies that that quadratic equation will only have one real solution. It's a repeated root, okay? That causes us to run into some problems because that only gives us one solution to work with. Because we have a second order equation, we need two solutions, and we also need them to be linearly independent before we can come up with our general solution. But that's why we talked about 4.2. Remember, what we did in 4.2 is we showed that in the case where you have a solution to a homogeneous equation like we have here, we can use this with reduction of order to generate a second solution, which is already guaranteed to form that fundamental set of solutions. It's already going to give us linear independence by the formula that we use. So we talked about that in 4.2. I don't need to rederive any of that. And we'll use that in a moment. But one other thing that's worth noting here, if y equals e to the kx is our solution, which came from k being that one real solution that we get from our auxiliary equation, what can we say about k? We can actually be a little bit more specific about the form of k because, again, this is coming from this is the solution to a quadratic equation, and one way to solve any quadratic equation is to use the quadratic formula. So that solution k could have come from this formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Our assumption at the very beginning was that the discriminant, this thing under the radical, was equal to 0. Plugging 0 in for all of that reduces this whole thing down to negative b over 2a. So k, our one solution, is just negative b over 2a. Okay, now what I'd like to do is take that differential equation and apply our reduction of order formula to that. Remember, the reduction of order formula requires your DE to have a leading coefficient of 1. The y double prime term has to have a coefficient of 1 on it. So originally our general equation had an a here. If I divide everything by a, this is what that ends up looking like. Now, in order to use reduction of order, we need a function that we call p of x, and that comes from the coefficient on this y prime. Remember, again, from 4.2, that's part of the formula we derived. So in my case here, P of x, which needs to be used in that formula, is equal to b over a, the constant b over a. But compare that to k. This is equal to -2 times this. So my function P of x, although I'm calling it b over a here, I could also call it -2k. Let's use that, okay? Now we go to that formula that we derived in section 4.2. So the second solution that I'm going to get from my first solution is equal to my first solution, e to the kx, times the integral of e to the negative integral of p of x dx. Okay, so the negative of this would be positive 2k. That's what I'm getting here. All over my first solution squared, so e to the kx squared dx. Now this is just a constant in my integrand here, 2k. So integrating that with respect to x, and remember we ignore the constant of integration, or we set that constant of integration equal to 0 when we do this. That would just give me e to the 2kx up here. I also get e to the 2kx down here because I'm using that exponent property, and so this gives me a 1 here, meaning my integral is just the integral of dx, which we know is x. This whole thing simplifies to e to the kx times x, or x e to the kx. This would be my second solution to that homogeneous equation, and we know from 4.2 that this will always automatically form a linearly independent set when we put it in with the first solution. So we don't need to use the Wronskian to check that we have linear independence. It's already guaranteed. That means our general solution in this case is y equals c1 e to the kx, there's my first solution, plus c2 x e to the kx. That's my second solution. Okay? There we go. Now we move on to case 3. And case 3 is an interesting one. Because case 3 involves complex solutions. We didn't have to consider complex solutions in case 1 and 2. And here's the thing. When you start mixing complex numbers with calculus, you're entering a territory that you technically have not learned yet. If you've only been through the calculus series, calculus 1, calculus 2, even calculus 3, none of that talks about how to deal with derivatives or integrals or limits or series or anything like that with complex valued functions. It's always assuming that the variable is a real number. Now, that doesn't mean that we can't do those things with complex valued functions, but that's covered in a course called complex analysis, or some undergraduate level courses just call it complex variables. It's a very, very interesting area of math. Something I have spent a great deal of time studying, and we can't assume anything from that because we're dealing with real valued functions in this course. So I need some way of manipulating the stuff that I see with complex numbers in the solutions for my auxiliary equation to give me real solutions, not complex solutions. In order to do that, we need a tool. We need something called Eulers Formula, which you may already know. You may have learned this before. But if you haven't, I'm going to show you where it comes from right now. When complex numbers enter the picture, very interesting things start to happen. We see functions that don't appear to be related suddenly having very, very close relationships. And what I'm talking about here are the exponential function e to the x and the functions sine and cosine. From Calculus 2, you learn what the Maclaurin series for each of these functions are. This is the Maclaurin series for e to the x, sine of x, and cosine of x. Okay, so this should be familiar from Calculus 2. Now, what I want to do is think about what would happen if I substituted a complex number in for x. Specifically, I want to plug in ix. Okay, so I times a variable x. What happens if I start introducing complex numbers into this? Well, we have to make some assumptions because, again, I can't assume that anybody has had complex analysis in this course, but we have to make some assumptions about, convergence and things like that when you start putting complex numbers in for here. Because none of the theorems that you talk about in Calculus 2 guarantee that those results work when complex numbers are used. However, it turns out that they do behave the way that we would expect them to. Okay, so without going into that, I'm going to make some assumptions here. I'm going to take e to the x, and I want to plug in ix into its Maclaurin series. So if that, I have my Maclaurin series on the previous page, what would e to the ix look like? Well, it would be 1 plus ix instead of x, plus ix squared over 2 factorial instead of x squared, plus ix cubed over 3 factorial, and so on. Okay, you see where all the i's are coming in. It's at this point that we need to remember how the imaginary constant I works. By definition, I is the number that you can square to get -1. And in fact, we have some other, this is always talked about usually in an intermediate algebra course where you're introduced to complex numbers. You learn that I to the first power is equal to I to the second power is equal to -1, I to the third power is equal to -I, and then I to the fourth power is equal to 1. And then if I raise I to the fifth power, it takes me back to the start again, and we have this infinite cycle. I, -1, -I, 1. I, -1, -I, 1. It keeps going with that cycle, that pattern, okay? I need to use this to simplify what I'm seeing here. So ix squared is the same thing as I squared x squared, but I squared is equal to -1. So this becomes -x squared over 2 factorial. The I cubed that I'll get from here is equal to -I, and I can pull that out into the front of this fraction here. So this becomes -I x cubed over 3 factorial. And then following that cyclical pattern, I'm going to see that these terms come out as I'm seeing them here. Plus x to the fourth over 4 factorial, plus I x to the fifth over 5 factorial, minus x to the sixth over 6 factorial, minus I x to the seventh over 7 factorial. Now, again, we're making some assumptions about convergence properties when complex numbers are involved. But just like the Maclaurin series for e to the x when x is a real number, this thing has this thing will converge absolutely for all values that I plug into it. And absolute convergence in a power series like this allows us to rearrange the terms of our sum without affecting the end result. So I can rearrange these terms, and if I take, for example, 1, skip a term, minus x squared over 2 factorial, skip a term, plus x to the fourth over 4 factorial, skip a term, minus x to the sixth over 6 factorial, and so on, group those up over here. And then if I take all of the terms with i's in them, ix, -I x cubed over 3 factorial, plus I x to the fifth over 5 factorial, and so on. If I group those up and factor that common factor of I out, look what I have. In this first set of parentheses, I'm seeing the Maclaurin series for cosine of x. In this second set of parentheses, I'm getting the Maclaurin series for sine of x, and then there's an I being multiplied to that. So this reduces down to cosine of x plus I sine of x. And what we have here is what we call Eulers Formula, condensed down right here. E to the ix equals cosine of x plus I sine of x. This is showing that when complex numbers enter the picture, the exponential function is intimately related to these trigonometric functions, even though they appear to come from completely different parts of math. Even more interesting is what happens when you start plugging certain numbers in for x. This is an identity, which means this will be true for anything I plug in for x. And if you happen to plug in pi, this side becomes e to the I pi, or pi I. You can rearrange that if you want. Cosine of pi is -1. Sine of pi is 0. So this whole thing reduces down to e to the pi I equals -1. Or if you add the 1 to both sides, e to the pi I plus 1 equals 0. You do not need to know this, this little equation here, this equality for this class. In fact, by itself, that equality is not exceptionally useful. Euler's formula is, but just this one consequence of Euler's formula is not particularly useful, but just take a second to look at it. There's only 5 numbers involved here, e, pi, I, 1, and 0. But these are arguably the 5 most important numbers in all of math. You have e, the base of the natural logarithm. You have pi, which comes from geometry when dealing with circumferences and areas of circles. I, the imaginary constant. 1 is what we call the multiplicative identity. You multiply it to a number and it doesn't change that number. 0 is called the additive identity. I don't have to argue for how important the number 0 is. And then we have some basic, one basic operation here, two really, because I have exponentiation and addition, I guess multiplication with the pi and the I here, but very simple operations happening, establishing equality. All 5 of these numbers appear to come from very different areas of math, and yet all 5 of them are related in an extremely simple identity like this. An extremely simple, identity is the wrong word to use, relationship. We call that Euler's identity. I guess identity is the right word to use, I don't know. And this is considered by many, many people to be the ideal example of beauty in mathematics. Again, the 5 most important constants in all of math are related in an extremely simple way, despite the fact that they all come from extremely different places. I'm rambling now, so I'm not going to continue beating this dead horse, but I enjoy this little fact, and hopefully some of you enjoy that as well. Moving on, we don't need this. We really need Euler's formula. Okay, so we haven't even gotten to case 3 yet, but I'm laying some groundwork that's going to allow us to look at case 3 in more depth. Notice, as a consequence of Euler's formula, e to the ix equals cosine of x plus I sine of x. If I plug a kx, so a constant times x, in for the x here, that would look like e to the I kx, and then I'd substitute kx in for these x's as well. Cosine of kx plus I sine of kx. Okay? So here's something I could say if I were to plug a kx in. If I plug negative kx in, so that my left-hand side looks like e to the negative I kx, I would have cosine of negative kx showing up here, but because cosine is an even function, it absorbs those negatives. Remember, that's a trig identity. So that's the same thing as cosine of kx. If I plug a negative x in for here, when I have this plus I sine of negative kx that would be showing up, sine being an odd function allows us to pull negatives out, and so I'd have a minus here. My purpose for doing that is because I want to simplify these things in a very specific way. If I were to add these two equations, so add e to the I kx plus e to the negative I kx, then looking at what we have here, the I sine of kx and the negative I sine of kx would cancel out. I'd have 2 cosine of kx. Similarly, if I subtracted this equation minus this one, on the left, I'd have e to the I kx minus e to the negative I kx equals negative 2I sine of kx. And you can see where the cancellation would happen there as well. We're going to use those results in our analysis of case 3. Okay, so I know I spent a lot of time talking about that. Here's where that pays off. Suppose we're looking at case 3, where again, our DE has an auxiliary equation with 2 distinct complex solutions, which would also be complex conjugates. That's important, and that's also guaranteed. So that would imply that our solutions for our DE would look like this. y equals e to the a plus bix, and y equals e to the a minus bix. Those are going to be solutions to our DE. I don't want to use those because they have complex numbers involved, and like we were saying before, we can't assume that you have experience working with complex analysis. So we want to see if we can manipulate these solutions in some way to produce 2 more solutions that are only involving real numbers and are linearly independent. That's where the work up here is going to come into play. Okay, so our general solution that we could form out of these, but we don't really want, would look like y equals c1 times that first function plus c2 times that second. Remember, that's an infinite family of solutions. So I can pick values for the parameters c1 and c2 and plug those in to get specific solutions. If I were to do that, if I were, for example, to pick c1 and c2 both equal to 1, that produces this solution, e to the a plus bix plus e to the a minus bix. Now, again, we're going to assume a little bit here because we haven't worked with complex analysis in this class, but we're going to assume that the usual exponent properties that hold in the case of real exponents also hold in the case of complex exponents. In particular, I want to be able to say that this side is equal to this side. That's an algebraic property, and we're going to assume that it works. Notice all I did is I factored an e to the ax out, leaving me with e to the bix plus e to the negative bix. This sum is of the same form as this sum up here, and so that here should give me the e to the ax that I factored out times 2 cosine of bx. Okay, leave that there for a second. Coming down here, if I were to go back to my infinite family of solutions and choose C1 to equal 1, C2 to equal negative 1, then I get something very similar looking, but with a minus instead of a plus. That minus there is making an expression in parentheses here that's of the same form as this expression. So the end result is going to look like e to the ax times negative 2i sine of bx. Now, these two solutions I'm going to use in place of the original two solutions that I got to form my fundamental set of solutions. And in fact, I'm going to simplify them even more. Notice that this 2 can be brought out front, this negative 2i can also be brought out front, and either of those, even though this one involves the imaginary number I, either of those are just constants. Constants get absorbed into our parameters c1 and c2. So really, we can ignore the 2 and the negative 2i and just think of one of our solutions as e to the ax times cosine of bx, another solution as e to the ax times sine of bx, giving me this as my general solution down here. Notice no more complex numbers are making an appearance here. Now, I didn't show that those two solutions are linearly independent, and it's actually not difficult to do with the Wronskian. It's just a little bit messy, and for the sake of time, I'm not going to go through that, but I encourage you to check that on your own if you want the practice. Okay, so we have now covered all three cases that can occur with that auxiliary equation. In the next video, we'll start looking at examples where we can start applying this stuff.